Hello everyone, I'm Ritali Ghosh, a graduate student at the Indian Institute of Science. Today I'll be talking about our recent work on ram pressure stripping in clusters. Gravity can bind the interstellar medium but not the circumgalactic medium. This has been published in the monthly notices of the Royal Astronomical Society. So let's get started. The environment of a galaxy plays a crucial role in shaping the distribution of matter around it. Let's consider an example of the galaxy GO206 in the galaxy cluster IIZW108. This optical image shows a number of satellite galaxies of this cluster which are moving through the cluster's potential well and through the diffuse intracluster medium that pervades the space around such galaxy cluster. The brightest cluster galaxy over there marks the center of the potential well. If we look at the satellite galaxy GO206 in multiple wavelengths, we observe some interesting morphological features. The H1 emission associated with the galaxy shown by the blue contours is highly disturbed, forming a long tail of neutral gas, while the stellar distribution is relatively unperturbed as seen in the black contour. This suggests that there is a hydrodynamic interaction going on which affects the gaseous component of the galaxy while the stellar distribution remains unaffected. A similar tail of displaced gas is seen in the H-alpha map observed with MUSE, the multi-unit spectroscopic explorer on the Very Large Telescope. The tails are characterized by both regions of diffuse emission and bright knots, perhaps from triggered star formation. Because of their peculiar morphology, the galaxies are popularly referred to as jellyfish galaxies. Numerical simulations in the recent times have done a lot of progress in understanding the evolution of the dense interstellar medium or the ISM of a galaxy with the intracluster medium or the ICM. When a galaxy is falling through the intracluster medium in its frame of reference, it would see the intracluster gas moving in like a wind. If we consider a Gaussian pillbox centered at the disk, the ram pressure pushes onto it and is proportional to the ambient density and the square of the relative velocity. On the other hand, the gravity of the disk provides a restoring pull which for an infinitesimally thin disk is proportional to the surface density of the stars, sigma star, and that of the gas, sigma gas. Therefore, ram pressure strips the gas from the interstellar disk at radii where ram pressure exceeds the restoring pressure. This is the classic Gunn and Gott 1972 criterion. A number of idealized simulations have intensively examined this scenario, providing valuable insights into the ram pressure stripping conditions. However, an inherent assumption is that the interstellar medium or the ISM of the galaxy directly interacts with the intracluster wind. But what about the circumgalactic medium? The circumgalactic reservoir is the diffuse extended halo of a galaxy which hosts the majority of its baryons, losing which would result in a significant loss of the fuel for star formation. In this work, we address the survival of the circumgalactic medium and study the coevolution of the galaxy's circumgalactic and the interstellar gas reservoirs. Our simulations are carried out in the 3D polar geometry of the Pluto code without radiative cooling. We assume the three phases, the ISM, the CGM, and the ICM to be isothermal. The galaxy is modeled as a rotationally supported disk at 10 to the power 4 Kelvin, surrounded by a 10 to the power 6 Kelvin stationary circumgalactic reservoir till the virial radius of the galaxy. A static gravitational potential is provided by the stellar disk and the dark matter halo. Beyond the virial radius, we initialize the ICM wind conditions with the velocities from bottom end to the top. I encourage you to check out our paper for more details on our equilibrium steady state initialization. Let's move on to the results now. This is a slice through our simulation domain showing the number density in logarithmic scale. The central dense disk is surrounded by this diffuse circumgalactic medium which progressively decreases in density as we go out to the virial radius marked by the circle over here. Beyond the virial radius, a dense ICM wind of 10 to the power minus 3 particles per cc at temperatures of 10 to the power 7 Kelvin with a velocity of 800 km per second pushes onto the circumgalactic and the interstellar disk. It first compresses the circumgalactic reservoir and then moves out both the circumgalactic and the interstellar reservoirs of this galaxy. If we looked at the zoom in regions, from the left to right, we have the slices of the number density followed by the velocity along the line of sight with pink showing gas moving away from us and green showing gas coming towards us, followed by the passive scalar advected with the fluid with the red color marking the disk in this panel, the CGM in this panel beyond the disk, and the ICM which is beyond the virial radius of the galaxy to begin with. And on the rightmost panel is the temperature. As we see the evolution, we find that initially it is the CGM which pushes onto the disk while the ICM is still not there in the picture. As we go along, we see now there is an interaction of the ICM and the CGM which continuously strips the cold gas out of the disk. However, as there is no radiative cooling, we do not see dense structures to survive in the tails. If we look at the mass evolution, in the left panel we see the disk mass as a function of time for various ram pressure strengths. For the blue lines in the different line styles, we have the same ram pressure but with different combinations of the number density and velocity. The similar evolution clearly states that the ram pressure determines the evolution of the disk mass. However, on the right, where the CGM mass is plotted as a function of time, we see that the blue lines are widely separated. So the same ram pressure doesn't give the same evolution for the CGM. So how do we understand the CGM stripping timescale? We find that it is the density contrast of the CGM with the ambient ISM density that determines its stripping. This is a sketch of the density profile of a galaxy cluster like Virgo, and for a galaxy with mass and size comparable to that of the Milky Way, the typical CGM density is marked over here. If the galaxy is moving at cluster outskirts, the density of the CGM can be higher than the ambient densities. This would mean that the CGM would behave like a cloud being pushed by a diffuse wind. There are two important timescales in the problem: the drag time, over which the cloud becomes co-moving with the wind, and it is proportional to the density contrast and the cloud size, and inversely proportional to the relative velocity. The second timescale is the hydrodynamic mixing timescale, which progresses faster as it is dependent on the square root of the density contrast. The galaxy can also be in an orbit where it passes close to the cluster core, and the typical ICM density can be higher than the CGM density. In that case, it would behave like a bubble which is being pushed by a dense wind. So what happens to it? To this end, we carry out additional hydrodynamic simulation, and this is a slice through our simulation domain showing the evolution of a bubble being dragged by a wind. We find that there is an initial hydrodynamic mixing at the interfaces, but soon enough the bubble is bodily dragged out of the simulation domain. The shortest timescale that appears in this evolution is the drag time, and it is proportional to the cloud radius and inversely proportional to the relative velocity, but independent of the density contrast. To summarize, if we look at the CGM mass evolution again, for the cases where the density contrast is greater than unity, we find that the slopes are very different. For the cases where the density contrast is less than 1, we find that the slope is independent of the density contrast as suggested by the bubble drag regime. I encourage you to check out our paper for more details on the bubble drag problem. You can also check out our cool 3D visualizations of this evolution by clicking on the link on the top right corner. If you have made it this far, thanks for watching. If you have enjoyed this content, hit the subscribe button and stay tuned for more.